being paid to just sit around.
And get fed.
Doesn't have to be
That's the NASA way.
Okay. So this will be lecture 16, right?
I think $30.
I also prepared my answers to for the online I'm gonna stay here after class.
It's a great job. Praise everyone.
Okay. So today we're going to study this Frobenius method, and it's just basically a modification to the Taylor series approximation method for the solution of second order ODEs. So what we have been doing is using a series expansion and then trying to use the differential equation to end up with a recurrence relation that will help us fix almost all of the coefficients on the series except 2. And but we said that method was only valid if the given differential equations variable coefficients p and q are non-singular. The Frobenius method is a small modification to this that would allow for certain classes of equations where these functions p and q are singular, it would allow us to get an answer. Okay, so given d second y dx squared plus px dy dx plus qx y of x is equal to 0, where px and qx may be singular. That means that they could go to infinity at any value of x. The point x0 is called a regular singular point if the limit when x goes to x0 of x minus x0 times dx is finite, and if this is an n, x minus x0 squared of qx or times qx is fine. Okay. So if I'm giving a differential equation and the functions p and q happen to be singular, but if those singularities are regular singularities, meaning that when we multiply px times the first order polynomial, we can actually get rid of that singularity. That means that the function px is 1 over a polynomial of degree 1. So it's a polynomial, or it's a function of x to the minus 1. And when we take a polynomial second order and multiply times q, we get rid of that singularity. Then we call those regular singular points. Okay? And if that's the case, then we can apply Frobenius methods. Then we can try a solution in terms of a Frobenius expansion as, so we can try y of x equals the summation from n equals 0 to infinity of an x minus x0 n plus k. So we can just add a value k, which may or may not be an integer, to the series, or to the power of the series. All right? So let's assume for a second that assume that x0 is equal to 0. Let's assume that the singularity occurs at x equals 0. And if that's the case, then y of x is equal to, which is equal to the summation from n equals 0 to infinity of an times x of n plus k will be equal to basically a0 x to the k plus a1 x to the k plus 1 plus so on and so forth. dy dx is the summation from n equals 0 to infinity of an n plus k x to n plus k minus 1. And the second derivative of y with respect to x squared is then summation from 0 to infinity of an n plus k minus 1 x to the n plus k minus 2. So back into ODE. Remember the ODE that was given is the second derivative, so that would be summation from n equals 0 to infinity n plus k minus 1 x n plus k minus 2. And by the way, notice that when I take the derivative of y and the second derivative of y, the summation doesn't change the initial index, because I don't know what k is. K might be just a decimal number, and maybe another integer, maybe a large integer, so we don't know what it is, so we cannot just simply get rid of the first term of the summation when we differentiate. Before, when we were doing the Taylor series expansion, the first term of the summation was just a constant, or a0 times x to the 0, which is just a0. When we differentiate that one disappeared, and therefore the first derivative, the first index in the summation disappears. Here we don't know what k is, so we cannot eliminate the first index, and here in the second derivative, therefore we cannot eliminate that index as well. So this is the second derivative plus px times the first derivative, which is n equals 0 to infinity of an n plus k x to the n plus k minus 1 plus q of x times y an x to the n plus k is equal to 0. Now we know, or we're trying this because we know that x0, in this case x0 equals 0, is a regular singularity. So recall that x0 equals 0 is a regular singularity. Therefore, we can assume the following. We can assume that p of x, whatever it is p minus 1 over x plus p0 plus p1x plus so on and so forth. And qx is equal q minus 2 divided by x squared plus q minus 1 divided by x plus q0 plus q1 x plus so on and so forth. So we can make that assumption. We can, because we said that in order for us to even try this method, those two functions, even though they're singular, they're regularly singular. That means that if we multiply this function times x, we should be able to make it finite, to make the singularity disappear. And that happens. When you multiply this function times x, notice this singularity disappears, and all you end up with is with a polynomial. It's an infinite polynomial. When you multiply this one times x squared, same thing happens. Okay? When you multiply qx times x squared, and that was the condition for a regular singular point. You multiply this one times x squared, you end up with an independent term, a first order polynomial, second order polynomial, third order polynomial, and so on and so forth. So that is a perfectly valid assumption. As long as x0 is indeed a regular singularity. So, therefore, let's see. I'm going to plug this definition of px in here and this definition of qx in here. So I'm going to have summation from n equals 0 to infinity of an n plus k, n plus k minus 1, x n plus k minus 2, plus px, which is p minus 1 divided by x, plus p0, plus p1x, plus so on and so forth. P minus 1, p0, p1 are just coefficients that make up that function px, and this multiplies an n plus k, x n plus k minus 1, plus qx, which is q minus 2 over x squared, plus q minus 1 over x, plus q0, so on and so forth, n equals 0 to infinity of an x n plus k, and all of these is equal to 0. So that's the given differential equation. All right? So if I evaluate the first term of each series, then therefore I am going to have a0, k, k minus 1. When n is equal to 0, I get a0, k, k minus 1. In this case, I'm going to get, when n is equal to 0, I'm going to get a0 times k times p to the minus 1 plus a0 times k times p minus 1 plus a0 times q minus 2 that's the first term on the series. Now I'm going to evaluate the second term on the series. When n is equal to 1, I get a1 times k plus 1 times k plus, and this is not really important, you can figure this out, k minus 1 plus anything that multiplies x to the k, and all of that is equal to 0. Recall that p minus 1 is the limit when x equals 0 of x times p to the x. By the definition, p minus 1, when we multiply everything by x, take the limit when x is equal to 0, we should obtain p1, or p minus 1. And q minus 2 is the limit when x is equal to 0 of x squared times q of x, by definition. And therefore, what I wanted to arrive at, the initial equation for k is k times k to the minus 1, or times k minus 1, plus k, p minus 1, plus q minus 2 is equal to 0. And that comes directly from here. So this is a quadratic equation. For k. And recall, once we have this, the solution n equals 0 to infinity, a n x minus x0 n plus k. All right. It's just a matter of finding the k's from this initial equation, and this is the k that will work for the Frobenius expansion. Okay. So let's look at a specific example, and you'll see how these make sense. By the way, rules for k. 1. If k1 is different than k2 and k1 minus k2 is not an integer, then yx is equal to c1 times y1x plus c2 times y2x, such that y1 of x is equal to the summation from n equals 0 to infinity of an x minus x0 n plus k1, and y2 is equal to the summation from n equals 0 to infinity of an x minus x0 n plus k2. All right? That is if the difference between the two roots of that initial equation is not an integer. Two, if k1 is not equal to x2 to k2 and k1 minus k2 is an integer. So if the two are separated by an integer value, then we cannot say that these two solutions are like this, because then these two solutions are not linearly independent from each other. They're essentially the same solution, separated by the power separated by an integer is just a shifted summation. So in this case, y of x is equal to c1 times y1 of x plus c2 times y2 of x, such that y1 of x is equal to the summation from n equals 0 to infinity of an times x minus x0 n plus k1, and y2 is a y1 of x log of x plus summation from n equals 0 to infinity of dn times x minus x0 n plus k2. And 3, if k1 is equal to k2, which is just equal to k, then again, y of x is equal to c1 y1 of x plus c2 y2 of x, such that y1 of x is equal to the summation an x minus x0 to the power of k, and y2 is x, summation from 0 to infinity of dn x minus x0 n plus k plus a y1 log of x. Okay, it's just the same as the previous one with an x in the middle. Okay, so we have three different options to express a solution depending on the nature of these roots, k1 and k2. All right? That was just a preamble, and now we're going to work on an example to show why this is relevant. Why are we even going through the trouble of coming up with a specific solution method for an equation that is also very specific. Okay? Because saying that we have an equation that is singular, but the singularities are such that when we multiply p times x, the singularity goes away, and when we multiply q times x squared, the singularity goes away, seems very arbitrary. It seems very specific. However, it is specific for a reason, because that particular class of equation is called the Bessel equation. And the Bessel equation is an equation that shows up everywhere. It shows up when you're solving the conduction of fluids problems or mechanics problems in cylindrical coordinates. It shows up when you're solving problems of heat transfer in fins of variable cross-section. That equation shows up all the time. So let's look at the equation first, see how it looks like, and then I'm going to go over some examples, maybe today, maybe Tuesday, of actual physical applications where you will see this equation showing up. Okay, so example. We have x squared, the second y, the x squared, plus x, dy dx, plus x squared, times y of x is equal to 0. Alright, that particular equation is called the Bessel equation of order 0. The Bessel equation of order 0. And you will see later where the different orders come from. But we can rewrite. We can divide everything by x squared. And notice that p of x is equal to 1 over x, and q of x is equal to 1. Okay? So this is singularity at x0 equals 0, or at x equals 0. This functions, well, one of them is enough, is singular. Okay, so notice that the limit when x goes to 0 of x times px is finite. It goes away. Singularity goes away when you multiply px times x. And how about when you multiply q times x squared? Does that go away too? Well, it's not singular to begin with, so if you multiply it by x or x squared, whatever you want, still non-singular, so this is also a finite result. this is a regular singularity at x0 equals 0. So we can determine the p minus 1 expansion point, which is equal to the limit when x equals 0 of x times px, which is equal to the limit when x equals 0 of x times 1 over x. The x goes with the x, and what is this? What is p minus 1? 1. And q minus 2 is equal to the limit when x goes to 0 of x squared q of x, which is equal to the limit when x goes to 0 of x squared times 1. So what is q minus 2? 0. It's finite. Okay, 0 is a finite number. So the initial equation remember is k minus 1 plus k times p minus 1 plus q minus 2 is equal to 0. Alright. So let's find k. K times k minus 1 plus k times 1 plus 0 is equal to 0. Therefore, k squared minus k plus k is equal to 0. That means that k squared is equal to 0. What is the solution of that equation? K1 is equal to 0 and K2 is equal to 0. So it's repeated roots. K equals 0. Right? So let's look for the, okay, so these are repeated roots. K1 equal to K2, which is equal to K, which is equal to 0. So we have y of x is equal to the summation from n equals 0 to infinity of an x n plus 0. K is equal to 0. dy dx is therefore the summation from n equals 0 to infinity of an times n times x n minus 1. And the second derivative of y with respect to x squared is then the summation from n equals 0 to infinity of an n minus 1 x to the n minus 2. Okay. So that looks like a regular Taylor series. It just happened in this particular case for this particular equation that k came out of 0 and all we have is a regular Taylor series. But that's just one of the solutions. Remember that case number 3, when the two roots are the same, we need to try a solution like this. Sorry, this would be n plus k. N plus k. We need to try a solution like this, n plus k, and then we need to try a solution of these form. So we take that and we plug it into the equation, back into the ODE. the ODE looks like x squared times the second derivative, so that's summation from n equals 0 to infinity of an times n minus 1 x n. And by the way, this is 1 and this is 2. Mistake. We cannot start that at 0 because the derivative of these never yield a 1 over x. It's minus 2, so this is starts at 2 plus x times the summation from n equal 1 to infinity of an times n times x to the n minus 1 plus x squared times the summation from n equals 0 to infinity of an times x to the n, and that's equal to 0. Alright? So I'm going to take that x squared and multiply it inside, and that will lead to n equal 2 to infinity an n minus 1 x to the n, plus I'm going to take this x, multiply it inside, this will be n equal 1 to infinity an x to the n, and I'm going to take this x squared, multiply it inside, an x n plus 2, and that's equal to 0. Alright? So then I'm going to take the first term in this series right here, n equal 2 to infinity an n minus 1 x to the n, plus the first term in the series will be a1 times x plus the summation from n equal 2 to infinity of an n x to the n plus the summation from n equals 0 to infinity an x n plus 2 is equal to 0. Alright? Then I'm going to take these terms right here. I'm going to combine these with these. These two series I'm going to combine. So I'm going to end up with a1 x plus the summation from n equal 2 to infinity of an times n minus 1 plus n x to the n plus the summation from n equals 0 to infinity an x to the n plus 2 is equal to 0. Alright, well this is n squared minus n plus n, so one of the n's goes away. I'm doing this in multiple steps. Again, a1x plus the summation from n equal 2 to infinity an squared x to the n plus the summation from n equals 0 to infinity of an x to the n plus 2 is equal to 0. And then I'm going to switch this n right here to m, so that when n is equal to 2, m is equal to 0. So I'm going to let m be equal to n minus 2. Therefore, n is equal to m plus 2. So we have a1x plus the summation from m equal 0 to infinity a m plus 2, m plus 2 squared, x to the m plus 2, plus summation from n equals 0 to infinity, a n x to the n plus 2, and that's all equal to 0. Now I can switch back to n, switch back to n, and join. Join the two summations, so you can just call this index n, and since both are of x to the n plus 2, you can combine them. So this is a1 times x plus the summation from n equals 0 to infinity of, and we have, let's see, a n plus 2 times n plus 2 squared plus a n, that multiplies x to the n plus 2, and that's equal to 0. And now we can make the same decision that we made before when we were using Taylor series, is that for a non-trivial solution, well, first of all, a1 needs to be 0. Because if the left-hand side is equal to the right-hand side, there's no x's on the right-hand side, nothing multiplies x on the right-hand side, a1 needs to be equal to 0, and a n plus 2 times n plus 2 squared plus a n must be equal to 0, which means that a n plus 2 divided by a n is equal to minus 1 over n plus 2 squared. This is the recurrence relation. So because we found that a1 is equal to 0, this recurrence relation is also telling us that a3 is equal to 0, right? That a5 is equal to 0, that a7 is, all the odd values are equal to 0. So since a1 is equal to 0, then a3 is equal to a5, which is equal to a7, which is equal to so on and so forth, which is equal to 0. So when n is equal to 1, a3 is equal to this times a1, and a1 being 0 makes a3 equal to 0. And you can say the same for a5, you can say the same for all the odd coefficients. So, for n equals 0, we have a2 over a0 equals to minus 1 times 2 squared. For n is equal to 2, we have a4 over a0 is equal to minus 1 divided by 2 times 2 squared. Well, it's 2 plus 2, sorry, which is equal to minus 1, 2 times 2 squared. When n is equal to 4, we have, I'm sorry, this is a4 over a2. a6 over a4 is equal to minus 1 over 4 plus 2 squared, which is equal to minus 1, 3 times 2 squared. And by the way, since a4 over a2 is minus 1 over 2 times 2 squared, then you can say that a4 over a0 is equal to 1 over 2 squared divided by 2 times 2 squared. And because a6 over a4 is minus 1 over 3 times 2 squared, then you can say a6 over a0 is equal to minus 1 divided by 3 times 2 square, 2 times 2 square, 2 square, and so on and so forth. So, now the series y1 of x, is the first solution that we're going to try, is the summation from n equals 0 to infinity of an times x to the n plus k, such that k is equal to 0. And we just found that because of the recurrence relationship, this will be a 0 times 1 minus x squared over 2 squared plus 1 over 2 times 2 squared times x to the 4 divided by 2 squared minus 1 over 3 times 2 squared times x to the 6 divided by 2 to the 6, and so on and so forth. I mean, this is not obvious, that recurrence relationship, you can collapse those numbers into these. Well, you see the 2 keeps repeating in the denominator, and the powers keep increasing, so it ends up being like that. So at the end, y1 of x is some integration constant times n equals 0 to infinity of minus 1 to the power of n. That switches the sign. See, when n is equal to even, you get a plus. When n is equal to odd, you get a minus, divided by n factorial squared times x divided by 2 to the power of 2n. And that's a solution. Well, that's one of the 2 solutions. Right? So remember, we have 2 values of k. We need we have 2 solutions to second order equation. But k is repeated, so we have to try this first. And the other one will be made up by these. So this seems like an inconspicuous function. This is an infinite series. It only has the even terms. That would be kind of the cosine. Okay. The cosine also has flipping signs. Okay, so you can kind of write the cosine like this. But the cosine has the n factorial. It doesn't have these 2. It doesn't have the n factorial square, it has just n factorial. And it doesn't have these 2. Okay? So the cosine will be minus 1 to the power of n divided by n factorial, x to the power of 2n. That is the Taylor series for a cosine. So this is obviously different than the cosine, and this receives a name. This is called the Bessel function. Okay? Because the equation is called the Bessel equation, the guy who solved it named these the Bessel function. So this is called J0 of x is the Bessel function of the first kind of order 0. Because the solution comes from the Bessel equation of order 0. If we change the order of the equation, not the order of the differential equation, it's not that we're going to make it a third order equation. I'm going to show you how the order changes. But this is the equation, the Bessel function of the first kind. The first kind meaning that it's the first solution, k equals 0. And this solution looks like this, or this function. If if you were to plot it in MathCAD, obviously you cannot plot an infinite series, right? You gotta truncate that series at some point, make it 100, right? Or you cannot make it 100 because MathCAD will crash. You know what it would crash? Huh? No, it's not a memory issue. What is the factorial of 100? It's too high of a number. So computer cannot evaluate the factorial. The computer cannot evaluate the factorial of 20. It's too big, too large. Okay, it's floating point unless you do quadruple precision and so on. But in double precision, your limit is what is it? 10 to the
Was it
Well,
18?
16 digit precision.
yeah, but that's the floating point precision. But the highest number you can represent in double precision is 10 to the 307, right? 10 to the 307. Yeah. And obviously that's a larger number. But that means that series decays very fast. The elements on that series decay very fast. So you can pick infinity to be 10, right? And then try to plot y1. So forget about a0. That's just a constant, right? The Bessel function is what's in the summation, right? And plot it. See what you get. And so you will get this. This is y, this is x, and you'll get a function like this that decays and actually intersects here exactly at 1. So this is a function j0. And the roots of these, it's not like the cosine where the roots are all periodic. The roots of the cosine are every pi. The cosine function hits the x-axis. In the case of the Bessel function, these roots are not periodic. They keep crunching against each other. This is mu01, this is mu02, this is mu03, this is mu04, mu05, so on and so forth. So those are the roots of the Bessel function. So roots mu k comma n. So this is the nth root of the qth order Bessel function. Nth root of the qth order Bessel function. Alright, so as a function, now you can try these series in MathCAD or MATLAB or whatever, and you'll find that it evaluates to that. Or you can just tell MATLAB, plot j0 of x, and it will have it in the libraries because it's a known function that is very useful for heat transfer problems in particular. Okay, so that's solution y1. Remember the solution y is c1 times y1 plus c2 times y2. Second solution. Remember, K1 is equal to K2, which is equal to 0. Y2 of x is equal to y1 of x times the log of x plus x times summation from n equals 0 to infinity dn times x to the n. Now, I'm not going to go through the process of finding the recurrence relationship and so on, leading to y2 of x is equal to 2 over pi the log of x over 2 plus gamma times j0 of x plus the summation from n equal 1 to infinity of minus 1 to the power of n plus 1. So this one means that it's alternating signs also. X to the 2n, so this one means that it also has only the even terms on the series, divided by 2 to the 2n n factorial square, and multiplying a series that looks like this. It's a really weird function, but that's the analytical solution. And this, not surprisingly, is called y0 of x. This is the Bessel function of the second kind of order 0. By the way, gamma is equal to 0.5772, there's a 7 here, 72, so on and so forth. Remember what that is? Have you ever seen it? 5772. It's an irrational number. It's called the Euler constant. Not E. E's not for Euler. E is an Neperian number. This is called the Euler constant. Okay. And the function looks like this. That's why it is singular. And it has infinite number of roots. It oscillates around the x-axis. Those roots also bunch up. So this is wrong here. Actually, they get closer together. So this is y of x, y0 of x. And as you can see, it's singular at x equals 0. So, at the end of all this, we've defined two new functions that are the solutions of. So, x squared, the second y, the x squared, plus x, dy dx, plus x squared, y of x is equal to 0, has solutions y of x is equal to c1 times j0 of x plus c2 times y0 of x. All right. So these are the Bessel functions of the first kind and the second kind, both of order 0. Okay? And they are the solutions of these equations. This is called the Bessel equation of order 0. So what is the, oops, let's leave this here. What is the Bessel equation of order nu? That's an equation that looks like this. It's still a second order ODE, variable coefficient. That's a Bessel equation of order nu. Just adding that minus nu squared on the right hand side will make this the Bessel equation of order nu. We'll see why. If we rewrite, we have the second y, the x squared, plus 1 over x dy dx, plus x squared minus nu squared divided by x squared, y of x is equal to 0. Here is p of x, and here is q of x. Notice that the singularity, singular at x0 equals 0. They're both singular at 0. But that singularity is removable, it's regular. That means that if we multiply p times x, singularity goes away. If we multiply q times x, singularity, or times x squared, singularity goes away. So let's find the coefficients. Therefore, p minus 1 is equal to the limit when x goes to 0 of x times p, which is equal to, what is this? 1. And q minus 2 is equal to the limit when x goes to 0 of x squared times q, which is x squared minus nu squared divided by x squared. And this is equal to what? When x is equal to 0, where does that go? Minus nu squared. So this is indeed finite. Finite. So that singularity is regular. So then we can go back to the initial equation. That says k times k minus 1 plus k times p minus 1 plus q minus 2 is equal to 0. That means that k times k minus 1 plus k minus nu squared is equal to 0. That means that k squared minus nu squared is equal to 0. That means that k1 is equal to nu, k2 is equal to minus nu. Right? So those are the two roots of this equation, nu and minus nu. Okay, so now we have two options because we don't know what nu is. Nu can be any number depending on what equation we're given. Nu can be an integer. So if nu is an integer, we know they're different. Okay, unless if nu is equal to 0, we're back to the Bessel equation of order 0. We know the solution is j0, y0. So we don't have to worry about that. But if nu, we know that these two roots are different because nu cannot be 0. So if nu is an integer, the two are separated by an integer. So let's start with case A. So, 1, if nu is not an integer, then we have y1 is equal to the summation from n equals 0 to infinity of an x to the n plus nu. And after major manipulation again and finding recurrence relationship and so on and so forth, that's equal to a0 times j nu of x. And y2 of x is equal to the summation from n equals 0 to infinity of an x to n minus nu. Again, we take the derivative of that twice, put it in the equation, find a recurrence relationship, see how those coefficients relate to each other. And I'm going to call this one C1, just to avoid confusion. It can be any constant. And this one is C2 times j to the minus nu of x. So these are j nu of x and j minus nu of x are Bessel functions of the first kind of order nu and minus nu. So they can have negative orders. So 2, if nu happens to be an integer, then y1 of x is equal to the summation from n equals 0 to infinity of an x to the n plus nu, and this is c1 times j nu of x, so it's the same solution. Bessel function of the first kind of order nu, and y2 of x is equal to a times y1 of x times the log of x plus the summation from n equal 0 to infinity of dn x to the n plus nu, and that happens to be c2 times y nu of x. So it's that y nu of x is the Bessel function of the second kind of order nu. Okay. So if we want to know what these functions look like, j nu of x is a summation from n equals 0 to infinity of minus 1 to the power of n times x over 2 to the power of 2n plus nu divided by n plus nu factorial n factorial. So we're multiplying two factorials, which makes the denominator even smaller there. Okay? But that would only be possible, see, if nu is an integer. We can only take factorials of integer numbers. Right? So this is what j looks like. That's if nu is equal to integer. Or j nu of x is equal to summation from n equals 0 to infinity of minus 1 to the power of n x over 2 to n plus nu divided by n divided by gamma of n plus nu plus 1 n factorial. And that is pretty much the same thing if nu is not an integer. That gamma function is pretty much equivalent to the factorial function for non-integer numbers. Such that such that gamma function of y plus 1 is equal to the integral from 0 to infinity of x to the y e to the minus x dx. It's called a gamma function. The gamma function. Such that the gamma function of y plus 1 is equal to y factorial if y is equal to an integer. And you can find that gamma function of y plus 1 is equal to y of gamma of y, which is a recurrence relationship with factorials. The factorial of n plus 1 is n plus 1 times the factorial of n. Same thing. And the gamma function of 1/2 is equal to square root of pi. Some properties about the gamma function, if you're ever interested in, or you come across it. All right, so let's finish up with what y looks like. We show what j looks like. Now what y looks like. Quick. See, show that y is, yep, it's related to and the Bessel function of the second kind of order nu is equal to 2 over pi. This one is an even crazier function. Log is the Bessel function of the log of x plus the Euler constant minus 1 over pi summation from k equals 0 to nu minus 1 of n minus k minus 1 divided by k factorial x over 2 to the power of 2k minus nu minus 1 over pi summation from k equals 0 to infinity of minus 1 to the power of n h of k plus h of k plus nu. And remember, this function only appears when nu is an integer. So we don't have to make the distinction of what happens when nu is an integer and nu is not an integer. X over 2, 2k plus nu. And this function h right here is that series from j equal 1 to n of 1 over j. All right. So let's plot them out. Before I plot them, some properties. Of the Bessel functions. The Bessel function of the first kind of order j plus 1 is equal to 2 nu over x times the Bessel function of the first kind of order nu minus the Bessel function of the first kind of order nu minus 1. and the derivative with respect to x of the Bessel function of order nu is equal to 1/2 of right, which means that J0 prime, you can use this to say that J0 prime is equal to minus J1 of x. So these are important properties that you might need for the homework. Because there's an exercise there where I ask you to show this is the case. And the plots. So we know that J0 starts at 1. So this is J0 of x. And J1, actually, they all, after these, they all start at 0. So this is J1 of x. And J2 will start like this. And some trivia here. There's a bounding curve. They're bounded by 1 over the square root of x. And the Bessel functions of the second kind they're all singular. And they're all then start pushing to the right. So this is y0 of x, this is y1 of x, this is y2 of x, and so on and so forth. So that's how they look like. All right. So finish 5 p.m. So with these, you should be able to get to all the exercises on the homework. If I see that, because I'm not going to be able to complete the material that I had completed last semester, because last semester we had those hour sessions and now we have 50-minute sessions. So we had 3 hours of lectures last semester every week, now we have 2.5 hours. But I think up until this point, you should be fine. And then next time on Tuesday, we're going to solve some examples that are going to be good practice for the exam. Okay? All right. So if I find out that one of the exercises you might need something else, I'll post it or tell you not to worry about that exercise. But so far, everything should be good.